Okay, so welcome to part 2 of lecture 6. Um, and now I will really start the introduction to the modern quantum theory, okay? And as I said, at some point I will just drop this word modern because essentially, I mean, there is no reason to refer to the old after we learn the modern one. Okay, so um, the first topic that I want to discuss is to elaborate a bit more about this wave-particle duality. So we have seen that light behaves as a wave, but also behaves as a particle in different situations. So we could say, well, uh, what does it mean? Does it mean that light is a particle or a wave or both? The point is that this question, to some extent, makes no sense. Let me explain why. So, um, there was a discussion in the past about the nature of light, and people had different theories for it. And some people described light as a being of particles, as Newton did. But there was also a theory of light as being a wave. Okay, this I mean before Maxwell, right? And I mean both perspectives were giving reasonable results. So, for instance, when you learn geometrical optics and you describe how a light beam is reflected by a mirror, and you describe how the light beam is deviated when enters water and so on, you can describe those things just thinking of light as a beam of particles. But there are some phenomena that if you have just a beam of particles, then it cannot be, it cannot happen. They cannot happen. And there are there are two phenomena that are very characteristic about waves, and those phenomena are diffraction and interference. So let us assume that I have um, a place where I fill with water, and I start, I put my hand on the surface of the water and start shaking my hand, and I see that I start to, produce waves of water. Okay. Um, and then I take my other hand and start producing again new waves of water. So I have now two sources of waves of water. You can see, depending on how you do that, that before before I start the waving of my second hand, I had some waves of water with some amplitude and so on. And as soon as I started playing with my waving my second hand, I see that sometimes the amplitude can grow, but also the valleys, I mean, the places where the wave goes down can also grow. So I can make the amplitude grow, but I also can make, when I say amplitude, now I'm referring to to the the height of the wave. Um, and you can play with that. I mean, um, and you see that one wave produced by one source will interfere with the second wave produced by other source. So this is, and you see that these waves can go across each other. So you probably have learned when you study elementary physics that there is a principle, which is the principle of superposition. So if you have a wave coming in one direction and another wave coming in another direction, the mathematics that describe those waves will be such that you can take the function that describes the first wave and the function that describes the second wave and add those functions. So this is the superposition principle. Okay. And also there is the phenomena of diffraction that I'm going to describe to you in a second. But the interference and diffraction cannot be seen if you are talking about a being of particles. Okay? So people decided that in order to uh, figure out what is the nature of light, they should test whether a light beam uh, will feature this type of phenomena, namely interference and diffraction. And if not, then light could be taken as particle. But you see that for this discussion to make sense, we are assuming that either light is a wave or light is a particle. Why we do that? Because this is what we knew from the description of physical phenomena. So we didn't know a third option. Okay? So the point is that I'm saying that because when you want to describe something that you don't know, the first thing you try to do is to make it closer to something that you know. And if this is successful, then you can say, well, light behaves as a particle, or light behaves as a wave. And I can use my knowledge about particles and waves in order to describe them, to describe light. But the point is, maybe light is something much more complicated. And when I try to bring uh, 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 the phenomenon closer to my knowledge, I oversimplify it. And this is somehow what happens. And if you ask me if light is particle or wave, I think the most appropriate answer to that is um, light is neither a particle nor a wave. Okay? So if you say, well, light is particle and wave, this is different from saying light is neither a particle nor a wave. But it behaves, sometimes like a particle and sometimes like a wave. I think if you accept that, the description can go beyond what the paradigms that you know are, then it's way easier to understand and to describe those weird things. Okay. So let me continue on the discussion. So people said, well, if light is a wave, then we should see diffraction and we should see interference. And a person called Young devised an experiment, which was essentially a screen with two slits, and you pass through light, and well, light will just go to the other side, passing through those slits. Those slits were small and thin. And if light is a wave, then when passing through the slits, I will explain in more details that in this next slide, then we will see diffraction and interference. And I can put, a screen after the screen with the slits and see how light will illuminate this screen. And there I can see the interference pattern of light. So if I see an interference pattern, then I'll say that light is a wave. However, imagine now that light is a beam of particles. If I throw a beam of particles against two slits, well, a particle can go either through one slit or the other slit, while the wave is a delocalized thing that can go through both slits at the same time. So if I can then assume that if I throw a bunch of balls against those slits, the pattern that I'll see on the second slit will be totally different. And just by looking at these patterns, I can tell if light is a particle or a wave. So the experiment was performed, and they saw a wave pattern on the second screen, and it was then accepted that light was a wave. Later on, with the theory of Maxwell said, well, light is nothing but an electromagnetic wave. And then, I mean, it was crystal clear that light was a wave. But as we saw, the progress made by Planck, Einstein, Compton, and others disputed this conclusion again. So essentially, this discussion was made back then in the 17th century, and then people understood that light was a wave, and then those fellows realized that actually light might be a beam of waves, but these will contradict this experiment that I just described, the experiment of the double slit. So definitely there is something that we don't understand. And de Broglie was a bit more, let's say, non-intuitive in the sense that he said that actually there is nothing wrong with having a dual behavior. So sometimes it's a wave, sometimes it's a particle, and this is not a particular property of light, but a property of particles, atoms, molecules, and so on, of a soccer ball. Okay, a soccer ball can be a particle in the sense of being a localized object, or can be a wave. De Broglie said that. Okay? So let me move to the other slide and explain now in more details what I just told you in quite long some time of speech. Okay? So this is the Young experiment with classical waves. By classical waves, I mean, if you don't want to bother about light at the moment, just think of it as waves of water. Okay? So I have a source S that will emit waves. So this is the description of the waves. Okay? So there is a wave that propagates from the source, and I put here this screen that is drew here with two slits, slit number 1 and slit number 2. So these are two tiny holes that when the wave hits the screen, well, you know, part of this wave will pass through slit 1 and part of this wave will pass through slit 2. And this is what is a singular property of a wave. It's not a localized object. So the wave will really go through this entire region and pass through these two slits. And when you study physics of waves, there is a principle called the Huygens principle, which says that when passing through these tiny slits will behave as sources. And this is what will give rise to diffraction. So when the wave passes through slit 1, then slit 1, which does not contain a source, it will behave as a source. So it will emit the wave here that I'm seeing here. Okay? And the same occurs for slit 2. I will have now slit 2 behaving as a primary source of waves, and it will emit this wave described by these lines here. Well, you can see that part of the wave that is emitted by the source 1, that is given by this upper wave here, will interfere with the wave produced at slit 2. So there is this region here where I see that one wave is on top of the other, and therefore they will interfere. Namely, I can apply the principle of superposition. And this means that, well, this wave will still keep propagating, and this wave as well. And at some point, they will hit this screen here that has a detector. So this D here is a little box that moves up to down and down to up. So it oscillates here. And for instance, if you're thinking about waves of water, you can think of this detector as being, a small box that collects the water that arrives here, or, something that a tiny ball that when the wave arrives, the ball will go up or down depending on the amplitude of the wave. If you think about these waves as being sound waves, you can think of this detector as being a microphone, so and a speaker. So when the wave arrives here, then the microphone will amplify the sound, and in some places, this sound will be higher than others. Okay, there is a question in the chat. Actually, the effect of diffraction is not will not be visible if this distance here is too big and if the slits are too big. So this must be of the order of the wavelength. Okay. Constructive or destructive? What is that? What is the question? So the waves, okay, I think I got your question. So the waves interfere, and in some places the interference will be destructive, and in some places it will be constructive. So there is not, a wave that for all the points of space, they will interfere just in one way. They interfere in different ways for different points, okay? So in some points, the interference will be constructive. So you amplify the amplitude of the wave. In some place, it will be destructive. So one wave comes with some height like that, and the other with some height to the opposite direction, and the interference is such that it is destructive. So it's not just a single type of interference, but at some point there are several different ways of interfering. Okay. Okay, so this is the setup, and this is the setup that essentially confirmed that light was a wave back then in the, I think in the beginning of the 19th century. But we can do this experiment again, and for the moment, let's just think about classical waves, and to avoid the confusion with light, this is just a sound wave or a water wave and so on. Okay? In order to understand what you're going to see, we can perform this experiment by parts. So in the first moment, I close slit 2. So I close this slit here and just let the wave to go through slit 1. Well, you see that I can draw now a plot here. So this is a plot. It is in a weird position, so it's a rotated plot of the intensity that is detected in this screen, namely the intensity that is measured by this detector, against the position on the screen. Okay? So when I close just slit 2 and leave slit 1 open, I see that this wave that passed through slit 1 will arrive at this screen here in such a way that the intensity will be higher when I'm looking at the position in the line that connects slit 1 with the screen, and it goes down when I move far away from this line. So the intensity will be higher here, and will get smaller, smaller, and smaller when I get away. And this is pretty intuitive, right? So you imagine that if you turn on your flashlight against a slit, then in the direction of the slit, the light will be, the intensity of light will be stronger. And when you move apart, this intensity will fall. Okay. Now you can repeat the same experiment by closing slit 1 and letting slit 2 open. Well, the conclusion will be the same, except for the fact that now the intensity will be higher here. So you see a plot of this type. The intensity is greater in points in the direction of slit 2, so essentially here, in this direction here, and will get less and less intense when you move far away from this line. Now I leave the 2 slits opened, and what I observe in this screen is a behavior like that. Okay? So this is the behavior I see. There will be some points where the intensity is high, and then there will be some points that the intensity is so small that it's almost dark. And again, there will be a point where the intensity is high, and the intensity starts to decrease, and will go to 0, and then we go high again, 0, high. So I see a pattern of high intensity, very weak intensity, almost dark, high intensity, very weak intensity, high intensity. So I see this pattern on the screen. So if I think about this as being a wave, I mean a sound wave, then the volume will be high here, while here will be you not hear anything, and the volume will be higher here, and so on and so forth. Okay? This is the outcome of the experiment. If you perform this experiment with light, you see that. Okay? And this behavior that light has this, that the arrival of light on the screen is because light, when passing through slits 1 and 2, it interferes, and therefore you have this pattern here that is a pattern of interference. Okay, this thing of intensity almost vanishing and going high, and vanishing and going high, this is a pattern of interference. So this is exactly what one expects for a wave. Okay, so I see that there are some questions in the chat. Maxwell said this before: light is a wave. No, Young came before Maxwell, and yes, this experiment was made, by Young. So this thing that I'm describing here, this experiment, This is before Maxwell, okay? What Maxwell did was to say that light is an electromagnetic wave. So it's a wave, but it's not a wave of something weird. It's a wave made of electric and magnetic field. Okay? So this is what you see, and this makes, I mean, essentially impossible to believe that light is a beam of particles. Okay? So again, I'm emphasizing that here I'm dealing with classical waves. So I'm talking about what I would say macroscopic waves. And I don't want to enter into many details, but a wave is described by a function that depends on the position of space and time. Okay, so I can ask you, what is the amplitude of this wave in this point of space? So at t equals to t1. So you need two information. You need the instant of time, and you need the position in space where you want to compute the amplitude of this wave. So there is a function that describes to you what is the amplitude of the wave. And this function is what we call the wave function. So this is if you want to describe, for instance, a wave that moves on a string. So you have a string attached to something, and you produce a pulse. So there will be a propagating pulse. So you want to describe the deformation of the string with respect to the horizontal line, and this is described by a wave function. Okay? And the intensity of the wave is, by definition, the absolute value squared of this wave function. Okay? So if I close one of these slits, I can define the intensity of the wave by taking the wave function that describes this wave. So if I close this slit 2, I'll have a function. So if I close this slit 2, I'll have a wave function phi 1, and the intensity produced by the wave that passes through slit 1 will be the absolute value squared of the wave function 1. Okay? There is a question. When we sometimes look at CD, we see rainbow patterns. How to explain this? Is there a connection with light interference? Well, it is connected with this thing that we discussed in the previous week, which is the fact that you see the composition of light with different frequencies, namely different colors. So this is a material that it has, it makes light pass through a material, and therefore different colors will move with different speeds in this material, and it is reflected out. So you see different colors because you are going to have different frequencies moving with different speeds on a material. Okay, and you have this decomposition of colors. Yeah. Now, if I follow the mathematics of interference, I can ask you how to compute the intensity when the two slits are open, namely slit 1 and slit 2, and I want to compute I. Well, in order to obtain that, you have to take, and this must be, I mean, this is the key thing, okay? So pay attention to that. You take the wave function 1, you sum with wave function 2, and these, after making the sum, you take the absolute value and square that. Okay? So you sum the wave functions, okay? And the wave functions will have signs. So this phi2 can be negative, this phi1 can be positive. So when you sum the two of them, this will give a destructive interference. Okay? So you sum the wave functions, and after summing that, you take the absolute value and square. This is different, completely different, so be careful with that. With respect to take the intensity of the wave produced by slit 1, the intensity of the wave produced by slit 2, and summing them. Because I1 is the absolute value squared of phi1, and I2 is the absolute value squared of phi2. And the sum of these squares is not the same as the square of the sums. I hope this is clear for you. If not, let me know. Did you understand what I just said? Because this is very important. So just to repeat and to be sure that everybody follows that, if I want to compute the intensity of the wave that will hit the second screen with the two slits opened, then I have to add the wave functions, and then I take the absolute value and square. Okay? So this is not the same as taking the intensities I1 and I2 and adding them. This is very important. So if you know how to perform this calculation, then this is the mathematics that you are going to use. You have to do this calculation here, and if you know how to do this calculation, if you know how to add the wave functions and square them, you are going to reproduce this pattern that I'm saying here. And there is a question: can we extend this to more than two slits? You can extend this to more slits, and you're going to change the interference pattern. Yes. Not useful. What is not useful? Yeah. So what happens is that in order to distinguish waves and particles, you need, two waves. Is enough. Two slits is enough because you already see interference. So there is a question: what is the wave function sign referred to? Well, okay. So let me just give you a concrete example so that you can understand this better. So assume that you have, for instance, so here you have a string. Oh, sorry. Here you have a string. Here you have a string. Okay. And let's assume that this string is, it's you have some tension on it, so it is completely on the horizontal line, and this string is attached to some place here. Okay. Now I take the string, I hold the string here, and I will produce a pulse. Okay. So I can produce a pulse. Let me draw it with a different color. So I will produce a pulse. And this pulse now will move towards this direction with some velocity v. Okay? The wave function will measure essentially the height of the wave with respect to the horizontal axis. So if the wave function phi, so I can define a horizontal axis called x. Okay, And the wave function that I'll call phi will depend on x and will depend on t. So at a given time t and at a given position, let me pick this position here, and let me call this instant of time t0, okay? So at t0, there is a snapshot of my wave pulse, and this is the configuration. If I ask you what is the amplitude of the wave at time t0 and position x given by this dot here, you can say the wave function is 0 because the amplitude of the wave here is 0. But if I take now this point, you are going to say that the wave function has this amplitude here because this is what the wave function measures. Okay, but now I could produce a pulse that propagates with an inverted amplitude. Namely, I could produce a pulse that goes like that. Okay, and see, let's assume that the amplitude here is the same as the amplitude here. Phi will give me the information about the amplitude here. So it will be the same absolute value of this point, but with a sign inverted, because I took the convention that the deformation in this direction is positive and the deformation in this direction is negative. So if this pulse now moves in this direction and this pulse encounters the other, then if I sum the wave functions, they will give 0 because they have the same amplitudes and opposite signs. So they interfere in a destructive way, and I have to take into account the sign. Okay? Is that clear, Mahmoud? Okay. Then there is a question. How about if you have another hole? Are you going to use the same? If you have another hole, then you're going to superpose now 3 waves. So you have to have phi 1 plus phi 2 plus phi 3. Okay? How about if you have more and more? So now you want to have several slits. You're going to just add a bunch of phi's, okay? And take the absolute value and the square it. So the principle of superposition says that you just have to take all the wave functions, add them, and in order to compute the intensity, you just square it, okay? Okay. And yeah, so this is the principle. Okay, so the key point of this slide is to understand that if I have two waves that are propagating from slit 1 and slit 2, they will interfere, and the intensity in this screen is given by this expression here, which is not equal to the sum of the intensities of the waves produced when one of the slits is closed. Okay? Is that clear? I will just move to slide number 4 if this is clear to everybody. Okay, sure. So what is the conclusion that we get from that? Well, first, the intensity when the two slits are open is a non-negative number. But I'm worried how we represent that Qn. I didn't understand how we represent that Q1. What is Qn? Phi. So phi in L. So is this a capital I or L? I don't understand. 1, 2, 3, 4, and well, I mean, the beauty of the superposition principle is that the description of waves can be made by just taking one wave each time. So you just describe a single wave, and then you can just add them up. So you don't have to try to describe the very complicated system of several waves at the same time. You just describe a single wave, and then in order to find the resulting wave, you just apply the superposition principle that tells you that you can add up all the wave functions. So if you know how to describe one wave, it's enough. You just have to apply the superposition principle. Okay. So I12 is non-negative because you take the absolute value, square it, and so on. And it can vary from 0 to a maximum value, right? Because, as I said, phi1 can cancel phi2, so this will give a 0 intensity. But phi1 measures an amplitude of a wave, so it has a maximum value. Phi2 also does that. So when you sum the two of them, there will be a maximum value. So I12 can really have value equals to 0 when these waves interfere in a destructive way. But it can also have a constructive interference and produce a maximum. Okay. If we close one of these slits, the intensity at X on this final screen can decrease as well increase. What I mean by that? Well, as I said, the waves can interfere destructively or constructively. So when I close one of these slits, the resulting wave that will show up in the screen is such that the intensity grows after closing the second slit because there will be no destructive interference at that point. Okay, so the intensity can increase, but also it can decrease because it could have suffered rather a it can decrease because it could have suffered rather a constructive interference with the second wave. So when you close one of these slits, you can see that the interference pattern will change, and places that were dark can become bright, can become illuminated, but also places that were with high intensity, they were very bright, can become darker. So this can happen. Okay, and this again is a property of waves because they interfere. Okay, this is very, very important. And there is this final comment, which is if we gradually decrease the intensity of the source, so the source produces light or water wave or sound wave with some intensity, and I can decrease the intensity of the produced light, these fringes, namely these lines that we see on the second screen, will decrease the intensity as well in a continuous way. Okay, so if I have a flashlight that I can regulate the intensity of the light that it emits, I will see the interference pattern, which will be some illuminated spot, dark spot, illuminated spot, dark spot, and there will be some intensity for each illuminated spot. But if I decrease So fringes, by fringes I mean this. So let me use the drawing here. Sorry, the picture here. So if I close the slit and I have just one slit, then I see this pattern here. So here I'm sending some laser through the slit, and I see that the pattern is such that in front of the slit, I have this high intensity, and as I move away, the intensity decreases, and the intensity decreases, okay? This is what we expect. When I open the second slit, so now I have two slits, and I have this laser beam crossing the two slits. I will have you see here that I have illuminated spots and dark lines, illuminated spot, dark lines, and so on. And here, darker and, again, illuminated, but with intensity that is smaller. But you see that those illuminated spots are what we call fringes, okay? So they are the fringes that we call fringes, these illuminated spots. And you see that if now I started decreasing the intensity of the light sent by the source, then the intensity of the light that I will detect in the second screen, this is a picture, okay? This is not a drawing. This would decrease, so the intensity will get smaller and smaller, but it would vary in a continuous way. So I would not see like intensity, so it's bright, super bright, and then I change the intensity of my flashlight, and suddenly there is a jump to a smaller intensity. No, I see that the intensity is changing continuously, okay? So this is an outcome of an experiment. So I'm just describing what you see when you do this experiment. And actually, unfortunately, if this was an in-person lecture, we could try to make this experiment together. So maybe, I don't know. Yeah, I can try to think about how to do that. But so there is a question. The fringes are the points that have the highest constructive. Yes, exactly. So, well, not. You see that here I call this a fringe, but I also call this point here where you have some non-zero intensity also a fringe. So the intensity here is higher than the intensity here. So I cannot say that it is the highest constructive interference, because here is not, but this is still a fringe. But it is when the interference is not totally destructive, okay? That's the point. Okay. Is that clear to you? How to describe the Young experiment with waves? What happens? So the key message from all these things that I said today is to say that if I am throwing a wave against this screen with three slits, the pattern that I will see on this screen is described by something like that. Okay? And you see that in order to describe this pattern, I have to use the mathematics of the waves. So I have to use the concept of wave function, and I have to use the concept of interference. So this is how I compute the intensity of the wave that arrives on the second screen. Okay? Is that clear? Now I can repeat the experiment, the Young experiment, namely, I have this double slit thing. But instead, of throwing a wave against this screen, I will just place here my source in the source spot. I will place a cannon. And this cannon, well, it's a tiny cannon, so it's a really, it's not a real cannon. So it's a tiny cannon that will shoot cannonballs, tiny cannonballs, against this screen here with 2 slits. And the nice thing about this is that this cannonball, it can move its direction. So you can really rotate and shoot cannonballs in every directions for some range of angles. Okay? And this shooting is completely random. Okay? There is one thing that I require, though, is that the rate of shooting, namely the amount of cannonballs that will be shooted by this cannon, is constant. And now I can ask you, what will be the pattern of, so if I now have a detector here, which can be just a box that collects the balls, I want to ask what will be the pattern of distribution of balls that I'll see in this screen. Okay, so one way of doing that, you know, this paintball. So these paintball guns, they shoot tiny balls of different colors, and when they hit something, they explode, and then you can see that you can see exactly where the ball hit a screen and which ball hit the screen, because they have different colors. Okay, so I can, this is also another way of doing these experiments. I can take a paintball gun and just shoot randomly against the screen, and I'll see the distribution, the pattern distribution of shooting, just by looking at different colors. Okay, but I can also describe this using a different concept, which is the concept of probability. Okay, because think about that. If I have to randomly shoot balls against this screen, I can ask you, what is the probability of finding a ball in one particular point of the screen? Or, to be a bit more careful, what is the probability of finding a ball in a tiny region of this screen? Okay. And let's assume that when the ball, for instance, goes through slit 1, if it hits a piece of the screen, it will bounce and so on. So it can happen that a ball comes here, hits this corner and goes down. It can happen. But if I close slit 2 now and just shoot randomly balls against this screen, I will see that it is more likely, the probability is higher to find balls collected by my detector in this region here than in this region here. Okay? So this is just a simple fact of an experiment. The same thing happens with the second slit. If I close slit 1 and I ask you, what is the probability of finding balls here and here? You tell me that is more likely to find balls here, so I have a higher probability here. And here, the probability is lower. Okay, so there is a question in the chat, and I should close the session. Why is interested probability? Why not take an interest in the mass density of the particles present in this region? Why? So the advantage of studying the probability is that the probability is a concept that allows you, in quotation marks, to make a prediction. So if I shoot these balls against this screen, and you know how is the probability distribution along this screen, I can restart the experiment and say, well, what after shooting, I don't know, a certain amount of balls, what is the chance of getting balls in this region here? And if you have the probability, then you can compute that. But I don't want to rush about that, so I will come back to this point tomorrow, and I will, we will start tomorrow by revisiting this experiment and describing the probability issue, okay? And we are going to see that the outcome is very different from the wave, the situation where you had a wave. Okay, so thank you for your attention. I will close the session now. And tomorrow, we will finish the discussion of the Young experiment and start discussing about the formalism of quantum mechanics. Okay? So have a nice day and see you tomorrow.